Hello. I want to talk about a little bit about transferring of data between the serial ports, and the cores of these the two major DSPs we have as far as the core of the bit depth inside the DSP cores. Over here, I have a chart showing us this is 2's complement, positive numbers of 4 bits only, positive and negative, with the sign bits showing a 1 means it's a negative number, positive, the sign bits is 0, and then I have the decimal representation. Well, actually, I guess that's hexadecimal as well because I didn't get above. But anyways, here's what I've drawn on the earlier DSPs, the ADAU 1701, that family, and the ADAU 1761, that family, are 28-bit DSP processors. So in the core, when it's doing the math and storing the data, it has 28 bits. Now the serial ports going in and out of the part, if you're or even the converters and the DACs, they're 24-bit ADCs, they're 24-bit DACs. The serial ports, they can handle 16-bit, but let's just call it 24 bits at the moment. So it's pretty much treated the same. And so we have 24 bits coming in and out of the serial data ports. So how does that map to the core? And what happens when it transfers is what we want to kind of discuss here. So up here, I showed you the serial port data, 24 bits. That means 3 bytes. I have it separated into 3 bytes, and I just put all ones. So it's a -1, 24-bit -1, because everything is a 1. The sign bit is a 1, and everything else is a 1. That means it's just 1 less than 0. It's all ones. So if we were to transfer this into the core, we would, obviously, the data would move from here down into the core. So I'd 3, 4, 5, 6, 7, 8. That byte gets transferred. 5, 6, 7, 8. That byte gets transferred. 4, 5, 6, 7, 8. That byte gets transferred. Actually, I got one less. Anyways, now what happens is there's I did mess that up. 1, 2, 3, 4, 5, 6, 7. Does it really matter? No. Anyways, there's 8. Yes, it does matter. So we transferred. In this case, it's a negative number. So we need to have the value in the core be a proper negative number. If we put zeros here, then the sign bit is going to be a 0. It's going to be a positive number. That won't work. So there's logic in the chip built in that if this sign bit coming from the serial port is a 1, it will fill this with ones. It will add ones, and that's called sign extension. It extends the sign, and so any negative number, any value below, everything is always a 1. It fills in ones. So you fill in the ones, and that'd be still a -1. Everything is a 1. Sign bit's a minus. If this happened to be a maximum positive number, where this was a 0, then this would transfer over to a 0. So the sign bit would be 0, and we would add zeros here. And we'd end up with that maximum 24-bit number represented inside the DSP as a positive maximum 24-bit number. The LSB of the serial port matches up with the LSB in the core. So this is for the Sigma 100 and Sigma 200 cores. If you don't know the 100 and 200 nomenclature, go to like one of my first videos that talks about the Sigma DSPs. And that's where I talk a little bit about the history of these cores. So, like I said, 28-bit core. Now, let's go on to the Sigma 300 and 350. These are the ADAU 1452 family. So 1452, 51, 50. And then the 1467 family, the 67, the 66, the 63, and the 62, if I'm remembering right here. So those are all 32 bits in the core. So more resolution. It's a lovely thing. So 32-bit cores, but the serial ports for the most part are still 24-bit. So which I neglected to write in here, 24 bits. 24 bits, in case you were wondering. 3 bytes, 24 bits. So we got to transfer that into the core. Well, the designers did an interesting thing on this to help with resolution and have plenty of headroom, but yet help a little bit with the low end, with the noise floor. What they decided to do is shift everything over 1 bit. So when you do a transfer from the serial port out into the core, the LSB is always a 0. It'll transfer to 0 because there's nothing here. Then 1, 2, 3, 4, 5, 6, 7. The rest of these 7 transfer up. This one comes up as the LSB in the next byte. 2, 3, 4, 5, 6, 7, 8. This one comes up here, 1, 2, 3, 4, 5, 6, 7, 8. And then that one comes up here as a 1. And then we have 7 more bits here to represent a whole number. And so in this case, it's the sign bit was a 1, so we'd sign extend 1, 2, 3, 4, 5, 6, 7. We'd add 7 ones. So what we're doing is we're adding 1 bit to the bottom of this 24-bit word. We're adding 1 bit, and then we're adding 7 bits to the top and extending the sign. This ends up being, of course, there'll be another video. I'm going to talk more about fixed point, but this is why we have, when you don't talk about the sign bit, we end up with 4 bits to describe a positive number. And so the most we could ever do is 1111, which is a 15. So we cannot get a whole number bigger than 15 in the Sigma 100 and 200 cores. However, in these cores, we can go up to, we added the 0 here. We only have 7 bits, so we have 128. We can represent up to a positive 127, and we have 42 bits, 6 dB per bit. We have 42 bits, 42 dB of resolution above what we would call digital 0 coming in. So we have a ton of headroom in the Sigma 300s. This is more for another topic. Right now, let me still focus for another day, another video. Let me still focus on the transfer. So that's how we transfer in. What happens? We add a 0 to the bottom, and then we sign extend 7 more bits on the top. When we're going out from the core, out to the serial port, we're going to truncate this and move the sign bit back. And well, actually, we'll look at, if these are all 0s, then it'll just move the sign bit over and translate the numbers, and this LSB gets thrown away. And so that's why the noise gets tossed, and which is fine. So we lose that 1 bit, and we transfer these 24 bits down. The sign gets extended, and that goes down. And then likewise, what's easier here is these lower 24 bits get sent out to the serial port. The sign has to get brought back. Now, what happens? These are the saturators. What happens here, and this is important to know when transferring data, if to know when is a saturated, when is a negative number too big. Positive, it's easy to do. If we have any ones here, let's say I have 0, 0, 1, 0, 0, 1, 1, 1, etc. Well, this is a 24-bit number. We have a number that's greater than a 24-bit number. We have a 1 here. So that's going to, that number is too big to transfer to the serial port. So what gets transferred is a maximum positive number, which is a 0 and all ones. So if any of these bits, well, actually this included, if any of those bits is a 1, then what gets transferred is a 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, all the way across. So it'll be 7 F F F F F F, and you'll see that it'll be a 7 F F F, and because there was a 1 where there shouldn't have been. It was, the number was too big, and so we saturated. So in the positive direction. Likewise with this curve, any a 1, this has to be a 0 here. If any of these is a 1 in the positive, well, this is a 0. If it's a positive number, that'll be a 0. If the rest of these, any of these 7 bits is a 1, then it's going to transfer out as the sign bit's going to come over here to be a 0, and then 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Maximum positive number. Again, 7 F F F F F F. So that's on the positive side. On the negative side, it's kind of the opposite. That if let me erase this and erase some of this. If any of these bits, if there are zeros anywhere in here, including that one, it will transfer as a maximum negative, which is a 1, and then all the rest zeros, which would be an 8, 0, 0, 0, 0, 0 in hex. Because 1000 is an 8. You can't quite see it there, but -8. But yeah, it'll be 8, 0, 0, 0, 0. So yeah, so all of a sudden you look at your serial ports. I'm getting an 8. Where is this 8, 0, 0, 0 coming from? When I have clearly a different number in here, that's a saturated number. So that's how the data gets transferred between the serial ports and the core.